Hi everyone, this is Python Data Science and Machine Learning at Scale. I am Rachel Oberman. I am a Intel AI Technical Consulting Engineer with a background in geospatial and data science from the College of William & Mary.
My name is Todd Tomashek. I'm an Intel Machine Learning Engineer. I'm the manager of the Python product and infrastructure team here at Intel. I've been here about 6 years, all on the Python team. Before that, I worked at the National Center for Supercomputing in Illinois.
Hi, I'm Albert DeFusco. I'm a data scientist and product manager at Anaconda. Since 2016, Anaconda has shipped the math kernel library MKL as the default BLAST library. In this talk, we'll discuss how Intel and Anaconda are expanding our partnership to take Python and data science to the next level across heterogeneous hardware. Today, we'll discuss how Anaconda and Intel have partnered to bring even more high performance and high scalability optimizations and packages to the data scientists using Python. We'll show that these optimizations can be easily installed and activated. Now, let's take a closer look at the details of this partnership and what it means, and I'll hand it over to Todd.
Hello. Unlocking performance and scalability in Python requires working around the interpreter's global interpreter lock, or the GIL, and implementing the key underlying algorithms in native code. I've been with the Python project at Intel from the beginning, and we have maintained our commitment to two key principles: performance and usability. Unlocking performance and scalability in Python requires working around the interpreter's global interpreter lock, or GIL, and implementing the key underlying algorithms in native code. To achieve this, we've been connecting the data scientists' favorite Python tools, such as scikit-learn and pandas, to Intel's performance libraries, such as the Intel OneAPI Math Kernel Library and Intel OneAPI Data Analytics Library. Implementations in native code allows concurrency at multiple levels, such as vectorization, multi-threading, and multiprocessing that were previously unavailable to the Python developer. Further, Intel has been investing in accelerations across the data science pipeline rather than focusing only on one stage, such as model training. With data science reaching nearly every industry, end-to-end performance improvements are critical. You will see some of the breadth we offer, as well as a demonstration coming up. While these techniques are powerful, we do not want every Python developer to need to be an expert in C or C++ in order to gain these performance benefits. So we committed to foster usability by connecting them through well-known tools with only small code changes, if any. And that is a key reason we collaborated with Anaconda from the beginning. We wanted to enrich the existing Python ecosystem rather than fragment it further. The upcoming demonstration will show significant performance gains with simple steps. And finally, the open, active, and very talented Python community is really the driving force that is making Python the #1 language for data science, and Intel wants to empower the community's contributions. To help that, we have made our next generation OneAPI data parallel C++ compiler available on Anaconda's default repository. DPC++ is based on open, not proprietary standards, and allows programming across CPUs and GPUs. Let's look at an overview of all the AI and data science optimizations powered by OneAPI that Intel currently offers. As you can see from this graphic, Intel offers a wide variety of optimizations and tools for AI developers and data scientists. These drop-in accelerations are offered for all steps of the data science pipeline, ranging from tools such as Modin, which distributes pandas data frames in a single line of code change, to XGBoost and TensorFlow for increased training and inference accelerations out of the box, to even scikit-learn, which increases scikit-learn models, inference, and analytics tools with only a few lines of code added. We will not get into the details of everything listed on this page, but as you can see, Intel has optimized and created a lot of ways to improve AI developer and data scientist workloads. Underneath, these optimizations are powered by OneAPI libraries, such as OneDAL, OneDNN, OneCCL, and OneMKL. But users typically do not need to interact directly with these packages in order to see scale and performance benefits. These offerings are either directly available on Anaconda's default channel, or they're compatible with Anaconda installations. The data scientist developer tools are also available to download together as a bundle through the OneAPI AI Analytics Toolkit. There's obviously a lot here, so I'm going to hand it over to Rachel to give you some more specifics on the performance benefits that you can unlock.
Thanks, Todd. So now that we have given you an overview of what AI optimizations that Intel offers, we're now going to quickly look at what performance gains users should expect by using these simple drop-in accelerations. As you can see from this graphic, there is a lot of optimizations offered at every step of the data science pipeline, from data preprocessing to model training to model inference. And all of these optimizations you see here only require minimal code changes to achieve this kind of performance. Now, there are a bunch of numbers here. I'm not going to go over all of them, but I am going to break down a few just to get a better idea. We are going to start on the left with the data preprocessing section. As Todd briefly mentioned, with Intel distribution of Modin, you could see anywhere from 1 to 100 times performance increase by distributing pandas data frames. In particular, on a data science workload using the US Census 2020 data, we were able to actually see 38 times faster performance at the ETL stage of that workload. On that same census workload, by using Intel extension for scikit-learn and simple two-line code change drop-in, we were actually able to see 21 times faster model training and model inference. Now, I'm just going to call just a few other numbers on here. With that same Intel extension for scikit-learn, you're actually able to see up to 100 times and even sometimes even faster model training and model inference with just adding 2 lines of code to your already existing scikit-learn workload. With deep learning frameworks such as PyTorch, by using our optimizations, you could see up to 1.55 times faster DLRM training. And with, again, those PyTorch optimizations, you are able to see up to 2.8 times faster DLRM inference. But what does this performance really mean? Before, you can look at megabytes of data, but now you could actually look at gigabytes and still iterate interactively, maybe even terabytes. It means you get a model back in minutes rather than hours. Let's take a look at a concrete example.
For this example, let's take a look at all the taxi rides in New York City. The full dataset is 30 months, which is 58 gigabytes. Typically, you start with a small subset to get going quickly. So let's just start with 3 months for now. That's only 6 gigabytes. And we'll start with your typical Python data science tools, XGBoost, scikit-learn, and pandas. Let's open up a typical notebook on my data science workstation. So, what do we want to know about New York City taxis? Let's try to predict how much rides will cost. Let's take a typical workflow. You load the data in once, then you spend lots of time understanding, iterating, and cleaning the data and extracting features. The better the data, the better the results. Then you will start throwing different models at it. Let's take a closer look at a few of these parts. First, let's look at the data. Let's see if there's anything weird about this data, like if there's trip times that ended before they even started. We need to get rid of these. What about really short trips that have crazy expensive prices? That's also weird. So we need to get these out too. Looking at a small amount of data, so this is pretty interactive, which is good because we spend lots of time with the data in practice. There's lots of steps that look like this, but I won't be showing them all today, as that would take way too much time. Now let's take a look at the modeling part. First thing I will try is to build a tree using XGBoost. Let's see how accurate this first model is. So the accuracy isn't good enough yet. The root mean square error is only 1.8. We have a few more models after this, but it's probably too little data to build a good model right now. So how about we scale up? I noticed that I have a few high-end RTX cards on my workstation. Maybe that'll help. I'll install the Rapid stack. This is the equivalent notebook in Rapids that we just ran. It's actually originally written by NVIDIA. We didn't modify anything. First thing we noticed is that the data won't fit in the NVIDIA GPUs, even though it's equipped with a huge video memory, 48 gigabytes each. To handle this large amount of data, we actually needed to learn Dask. There's lots of Dask concepts we needed to learn and lots of code we need to change. Let's take a look at a few snippets of this. For example, we need to map the data to partitions. We also need to manage data in memory. So lots of changes like this. I won't go through them all. We needed to start a Dask cluster and cuDF workers, learn the concepts like Dask features, and so on and so forth. So we do all of that and get Dask running just fine. Great. Let's try to train. All right, here we go. Not sure what's going on here. We actually tried a whole bunch of things, but just couldn't get it to work. We got different errors in different places during different runs. We even tried running on a pre-installed Rapids environment in AWS with lots of GPUs, and we didn't get any luck there either. So maybe it's time to try something different. So let's try to run the whole dataset again, but this time with the standard Python data science APIs that we used in our first notebook. But this time, we'll be pulling in all the latest and greatest software optimizations from Intel to be able to handle all of this data. So this is the same typical Python notebook like before, just a few extra imports, same familiar APIs, pandas, scikit-learn, and XGBoost. Let's now go look for the same kind of data anomalies as before. Okay, do we have trip times that ended before they even started? Yep, still here. What about really short trips that have unrealistically high fares? Yep, also still here. The same interactive experience as before. Milliseconds for each query, but hey, we're now looking at all 380 million taxi rides, all 58 gigabytes of data, 10 times the amount of data we used before, and still milliseconds with Intel distribution of Modin. Now let's look at our models. First, since we're training the tree on such large data, we need to make sure we have the latest and greatest XGBoost version. Intel upstreamed a whole bunch of optimizations over the years to XGBoost. With the latest 1.4.2 version, it only took 11 minutes. With 0.81 version, this takes almost 2 hours. That's the difference between doing a few emails in between runs versus waiting most of the morning for your results to come back. So just make sure you're not using an old XGBoost version that IT gave you or that old XGBoost version that you installed when you first got your computer. Now let's see if larger datasets made a difference. Yep, the accuracy did get a little better than our first notebook, from 1.8 to 1.7. But this is where I'd like to start trying other models. Let's try with scikit-learn. So it turns out simpler is better sometimes. I try a ridge regression using scikit-learn. The accuracy is much better, which I'll show in a few moments. And this model took almost a minute to run, which is okay, but we could do much better. Let's use Intel's extension for scikit-learn for this. To use it, I just import it and then turn on the optimization. This warning message shows that the optimizations are now on. Let's see how long ridge regression takes now. Wow, this only took 3.85 seconds, which is much faster. Awesome. So I don't need to worry about waiting for my model to run, which can get annoying when we keep tweaking our model over and over again. But do we still get good accuracy? Let's check and see. Yep, same accuracy as before. Intel has been working very closely with the scikit-learn community and making sure all of our optimizations yield same repeatable numeric results so that you get lots more experimentation in without sacrificing accuracy. So with these Intel optimizations, you can start doing data science at much larger scale and use the same exact APIs as before. And you can use the entire data set and still iterate with millisecond interactivity with a turnaround model in minutes, not hours. And now let's take a look at how to get all of these Intel AI optimizations, plus many more with Anaconda.
Now that you've seen the power of these drop-in accelerations, let's pass it back to Albert, and he could tell us how to get these kinds of optimizations with Anaconda.
Thank you. For a little more background on our partnership with Intel, as I mentioned, we've been shipping the MKL library as the default since 2016, and you can use Anaconda on any major platform and any major cloud provider. We call this Anaconda Everywhere. And in addition to shipping NumPy and SciPy with these optimizations, you can access more of the 1MKL functionality using packages like MKLFFT, Random, and DNN. As you've seen, the Intel EX optimizations provide a drop-in replacement for scikit-learn's functionality, requiring only one line of code to be changed after you've installed the Conda package. Further, we're announcing now the availability of several more packages provided with Intel optimizations. We've talked about Modin, and when you install Modin from the Anaconda defaults library, you'll get the Intel distribution with OmniSci on by default. If you want to dig more into the one API, you can install the DAL for Pi library. That's used to power the scikit-learn optimizations, and you can access more of the low-level optimizations, and in particular, you can build distributed machine learning algorithms with DAL for Pi. And finally, the MKL UMath provides optimizations for the universal functions deep within NumPy itself. And finally, you can now contribute to the one API Python ecosystem with the DPC++ compiler available right from the Anaconda distribution. You can install the compiler for Linux and Windows right into your Conda environments, or use it directly in your Conda build recipes by using the compiler shortcut here. You can go and build your own Conda packages using the best optimizations you can get. And now I'll hand it back to Todd to talk about what's coming up next.
Thank you, Albert. So what's coming up next? As I said, data science is very critical to the industry, and it's so critical that it's grown beyond CPUs and GPUs to even other types of accelerators. Intel's OneAPI offers the promise of heterogeneous compute across multiple different XPUs. For Python, we have Data Parallel Python, or what we call DPPY. DPPY is a single unified offloaded programming model using Python data API standards, Chronos, SYCL, and other extensions and technologies to bring the Python ecosystem to run on different types of hardware, or XPUs, all open standards and all open source. This means that users will be able to run their Python code using popular libraries such as NumPy, SciPy, XGBoost, TensorFlow, PyTorch, on multiple XPUs, taking advantage of the extended compute and memory on both the host and the device. As you can imagine, the technical challenges here are significant, but the outcomes are very exciting. We're leveraging the popular Numba Python compiler and OneAPI DPC++ compiler technology in order to keep compute on the right device and to minimize data copy penalties. DPNP, which is data parallel NumPy, DP control, and Numba DPPY packages are all part of the DPPY XPU package suite. And all those packages are currently available on the Anaconda Intel channel. They're also all coming very soon to the Anaconda defaults channel. Be on the lookout for more information on DPPY. Rachel?
Yep, thanks, Todd. Now, with all of this information on Intel and Anaconda's partnership to improve the Python AI ecosystem from this talk, we really encourage you to go out and install the Intel AI Python software from Anaconda for easy, fast, and scalable data science tools. On this slide, you will find more information on Intel and Anaconda's partnership, as well as resources for more information on specific Intel Python data science software options.